too big, your email accounts might not like it. So you might end up getting 4 or 5 messages with pericyclic reactions, you know, 1 message per lecture almost, because then the files are only about between 1 and 2 megabytes each. If you add it all together, it's about 80 pages of pericyclics, and then we've got the rest of the week to go. So, but we will send you my colleagues at GNDU will send you the material. Or if they give me the list, I suppose I could do it. Yeah. Okay, so cycloadditions we've looked at so far have been done a bit thermal. In other words, you don't need, so you just heat things up, or in some cases, if they go fast enough, mix the things together. We've seen some cases where reactions happen at 0 or even below. So I want to, and they're both cases so far, the Diels order reaction and the dipolar cycloadditions have been 4 + 2 cases, so 6 electrons, 4 pi + 2 pi. What about 2 + 2, 2 alkenes together, for example? Well, they don't work thermally, the orbitals don't match up, as we'll see in a moment, but they do work if you work by photochemistry. We've not said anything so far about how the orbital treatment deals with photochemical reactions, excited state reactions, and then towards the end I'll move on to the second category, electrocyclic reactions. So let's think about trying to get a concerted 2 pi + 2 pi cycloaddition. We can draw it like that, but it's not generally useful, and a quick frontier orbital analysis would tell us why. Thermally, we'd have to have a HOMO and a LUMO, so there's the HOMO of one alkene, here's the LUMO of another, and you just can't get, with a simple geometric approach, you can't get constructive overlap to form both bonds at once. So it doesn't work. Unlike the 4 + 2 case. And even if you turn the HOMO and LUMO the other way around, well, you get exactly the same result. So you get a clash, an anti-bonding or a negative, unconstructive reaction if you try to think about that thermally. So that's why we haven't mentioned it yet. You can get it to work if you don't use the face-to-face direct superfacial approach. One component would have to be anterofacial. You have to have a kind of right-angled approach, a kind of crossed approach of the two alkenes together, which really means you can't get such good orbital overlap anyway, because the orbitals can't overlap end to end properly. So it's very difficult to get that when you've got an alkene, because the substituents get in the way. But it works for humulines like ketenes here, where one end, if you like, doesn't have geometry of the substituents, it's just a linear molecule. So this works for cyclobutanes, for example here, with this as a 2 pi component and this as a 2 pi component, room temperature, you get the cyclobutane, the 4-membered ring, but as you can see, there isn't a lot of control over the stereochemistry here. So with the right examples where perhaps if you have one where these two substituents are the same, there isn't any stereochemistry to worry about. So it can be used in some cases, but you have to have a strange approach. So here's an attempt to try and show how that works for this kind of crisscross type approach. So here is there is the diene, and we're just picking one double bond of it, and that is suprafacial, so I'm forming both bonds on the top face of the diene, and that's why I can draw it the way I have. And here comes the ketene, and I'm going to draw the LUMO of that, and I'm going to try and do an anterofacial linkage. So So it's LUMO, because you can see that's like a pi star bond across there. But it means I've got to join this lobe to that one, and that one to that one, to get good interactions. And that means it's anterofacial across the, or opposite sides of the ketty. Geometrically, you can see why the overlap of that orbital, which is pointing in and out of the screen, and this one, which is pointing up and down the screen, that's not going to be such a good end-to-end sigma-type overlap. It's not a zero overlap, but it's not very good. Now, I've drawn that a complete right angle, which you can imagine little twists from that, which is harder to draw, but perhaps gives you a slightly better overlap. But nevertheless, it's possible to imagine bonding overlap there, which, if you like, is heading towards a kind of twisted product like that. And you can see why, if you have a large, that's L and S is meant to be large and small, the smaller substituent on the ketene would prefer to be on the underside of the screen as I've drawn it, closer to the diene than the large group, which would block more space there. So it can be done, and that's the sort of molecule you get out of it. It's not perfect, and it requires these rather special alkenes, which are not really alkenes anyway, but they don't have geometry at both ends. They don't have constraints at both ends. Because if you imagine if this was an sp2 center and there was another substituent here pointing down into the screen, into this 5-member ring, that would be quite sterically constricting. So it can be done, but only in these rather special cases. And then there is a debate about in these cases, is it really a concerted reaction anyway? But I don't want to go there. But the frontier orbital analysis says shows why you have to use this rather strange approach, which we've ignored anything other than a straight, simple-looking approach, suprafacial before. But if you do photochemistry, it is allowed, 2 plus 2. What is going to happen here is the light frequency, or energy, is such that it will be absorbed by one of the alkenes to promote one of the electrons from what was the HOMO to what was the LUMO to generate a first electronically excited state. So now we have what are sometimes called SOMOs, singly occupied molecular orbitals. So we have now in one of the two components, we have one electron going up into what used to be the LUMO. So let's see what that does. So here are the orbitals of one alkene that doesn't get excited. Now the chances of two excited alkenes meeting, the number of excited molecules is quite low. So the chances of both molecules both components being excited is quite low. So most of the reaction happens by one ground state molecule reacting with one excited state molecule, and that's been interacted with the light. So here's the unexcited molecule with its HOMO, 2 electrons in it, and its LUMO empty. Here is the molecule that gets excited. This is what used to be the HOMO, this is what used to be the LUMO, but one electron gets excited by interaction with the light, promoted, and so this is now HOMO star, if you like, it's the new HOMO. And sure enough, that interacts nicely with this LUMO here. So that's the frontier molecular orbital analysis. Here's the LUMO of the unactivated alkene. And here is the HOMO of the activated alkene. And this is the highest energy electron. It's the one that will have the most influence. But you could do the same if you interacted these two as well, where there are 3 electrons, but you'll still get a little bit of stabilization. But in both of those cases, you can interact straight across, because this is a filled and half-filled, this is a half-filled and empty, so neither of those are filled and filled interactions. But if you take the top one, the LUMO and star, new HOMO, again you get two constructive interactions. So they can both react suprafacially, so they don't have to do any twisting. So geometrically this is favourable. So that really explains why the photochemical 2+2 does work, while the thermal one didn't, except in the special cases. And actually that's all I want to say. There are some examples of this having been used in synthesis. What I really want to do is just to point out the difference between them. The thermally is allowed with 4+2, 6 electrons total. Photochemically, that's 2+2 is allowed for, photochemical is allowed for 2+2, but not for 4+2. So if you see photochemical 2+2 reactions, they work because of this, or because they're not concerted reactions. They're two-step reactions with intermediates and charged intermediates and so on, or maybe radical processes, but not via pericyclic concerted type mechanisms. They have to be photochemical to be concerted type mechanisms, or have this very twisted approach, and then that constricts you to things like ketenes, isocyanates, that sort of thing. Okay, so that's all I want to say about 2+2s. It's not so used in synthesis, but I do want to spend the remainder of this session talking about electrocyclic reactions, where we interchange one pi bond with one sigma bond. If you're ring closing, then you're converting one pi bond into one sigma bond, and that's what the top example is here, making a sigma bond here and losing overall one pi bond, rearranging the ones that are left. Again, stereochemistry is defined, so here we have an EZE triene and produces a cyclohexadiene with the two methyls on the same side. And if you have different geometries at the starting triene, then you have different geometries in the product, and we'll say a bit more about that in just a moment or so. The ring, whether it's a ring closure or ring opening depends on thermodynamics. So here, this one prefers ring closure because sigma bond instead of a pi bond is thermodynamically favourable. But there are cases where, in the four-membered ring cases, where it goes the opposite way. This is an illustration, a case that shows what is allowed thermally isn't allowed photochemically, and vice versa. We saw that with cycloadditions. So here, you can do the same kind of reaction photochemically, and the same is thermodynamically still favoured because we're swapping a pi bond into a sigma bond. But look at the result here. Same starting material, but under photochemical conditions, we get the opposite stereochemistry. So we have to be able to explain these kinds of differences. Well, first of all, explain any stereochemical control, and then explain the differences. Now, it's difficult to have two components here because it's just one thing undergoing reaction. So what we do is we look at the highest energy electrons involved and say that what happens to them will have the biggest influence. And so that means looking at the HOMO of, in this case, a triene system, to use the examples on the previous page. That's a 4n plus 2, 4q plus 2, whatever you want to call it, system. Thermal electrocyclization, in this case, it gives a disrotation. I'll show you what that means a little bit lower down. So here is the system. This is the triene HOMO when the process is thermal, so it's ground state HOMO. Looks like three independent double bonds. it's reacting by joining the two ends together, so it's those two ends. So let me draw it in a wraparound form, because these two ends have got to come close to one another if this is going to happen. And clearly there will be conformational changes necessary here, so if you have too many substituents around the outside, that may hinder it. But let's say it all happens. To get good overlap, that top shaded lobe there has got to rotate inwards to meet that top shaded lobe there, which has also got to rotate inwards. Those two rotations are in opposite directions. That one is, if you like, is clockwise, this one is anti-clockwise. They're in opposite directions, so that's what we mean by disrotatory or disrotation. Rotations in opposite directions, and that's what's necessary for this reaction to go, to get that orbital overlap, good orbital overlap here. And if you do that, rotating the left-hand one clockwise, and this R group will come up as it goes. If you do this one anti-clockwise, the R group will come up. So that's why with the E, Z, E triene, that one, you will get both R groups on the same side, because this rotation will bring them both up, or both down, and that gives the same molecule, just looking at it from behind the board instead of in front. So thermal electrocyclic processes will be disrotatory like this one. If the total number of electrons is 4n plus 2, or 6 here is 4n plus 2 with n equals 1. And it will be conrotatory if the total number of electrons is 4n, so in a diene or tetraene case. And actually it will all be reversed for photochemistry. Why? Because the highest, taking the same thinking, the highest energy orbital will now be one higher. It'll be what I've called HOMO plus 1. It'll be what used to be the LUMO, it'll be the next one up. And that has opposite symmetry. So you just reverse all the, so you go to photochemistry and you're talking about one orbital further up, and it has opposite symmetries. So conrotatory then is if it's 4n and they go in the same direction and it's thermal. Photochemistry is disrotatory with 4n plus 2, and, sorry, say that again. With photochemistry it's conrotatory with 4n plus 2 and disrotatory for 4n. Basically, it's the reverse of thermal. Now, rather than remember that, I always just write it down, because it's visual then to see what, as long as you've got the orbital phases right, just look at what's got to happen. All electrocyclic reactions are allowed, provided they're not constrained by the geometry of the product, in other words, the substituents banging into each other. The difference is whether you get conrotation or disrotation, which would produce different stereochemistry. So here's some examples. The pentadiene systems, 5 atoms, not 6 like in the last case. How does that work as a pericyclic reaction? Well, if you put a Lewis acid onto the carbonyl here, you can regard that as a pentadienyl cation, as a big enough contributor to allow a ring closure. It's 5 atoms, but it's only 4 electrons, those 2 pi bonds. So it's a 4n or 4 pi ring closure. So those are the curly arrows, and it's 4 pi, so it's going to be conrotatory thermally. So in fact, 1H will go down and 1H will go up. So that obeys the rules. The relative configuration of those 2 new asymmetric centers is controlled by the pericyclic reactions by a conrotatory process. And so that's there's an illustration of the 4n being opposite to the 4n plus 2, or 4 electrons being opposite to 6. That's a thermal reaction. This is trying to do it by the Woodward-Hoffman rules, which I don't want to get into. into. This is the looking at homo-lumo. Ignore, this is trying to break it down into two components, but if you look at this as if you were to draw the homo of well, I guess it is simple to make it into two bits. We're regarding it as an allyl. We've got to somehow incorporate the cationic, pseudo-cationic center. So we'll call that an allyl cation and that an alkene. So if you look at, so if you're going to pretend it's two bits, you can have a homo of the allyl cation and a lumo of the alkene, and it works conrotatory. You could also try and just draw the orbitals for a pentadienyl cation, which would give you the same result, conrotatory. So the thermal one is conrotatory. Photochemical, you could reverse it if you want the opposite. Harder to do photochemically, actually. Here's an anionic one. What's the difference? This would now be a 6 electron, because it's got 2 pi bonds and a negative charge. So here's a double imine made from a reaction of ammonia with a carbonyl group here, and then condensation with benzaldehyde. I've actually done this one, well, not I've done it myself, one of my research students did it, but it's an old reaction actually. And now we end up with the 2 substituents, which were both outwards here, same as both H's are inwards there, but you end up with the 2 substituents on the same side, whereas the 2 H's were opposite there. So that's because it's a thermal 6 electron this time, so a 4n plus 2 series, so it's going to be disrotatory. So this is 5 atoms, but 4 electrons, 6 electrons, and showing the opposite results. So I say in each case, just draw the orbitals down and think about it. So, for example, the trying one, draw the orbitals if you can't remember it, rather than remember this, which you might get wrong, badly remembering it. So those are 2 variants to show how the rules apply beyond the simple all-carbon case. Now here's, I think this is my final slide actually, here's a version of this that's very important to us all. So it's important in the formation of vitamin D in humans. It's why a lot of Asian people who come to the UK and don't eat as many, have a different diet to people born and bred in the West, don't produce as much vitamin D. They're not used to the reduced amount of sunlight that we have in the UK. So one way or another, they end up not producing as much vitamin D because the process that's going on here, sunlight is producing a photochemical ring opening of this system. It's a conrotatory electrocyclic ring opening photochemically. So a 6 pi system, or 6 electron system, triene here into converting with a diene and a sigma bond. So it's a 6 electron system, but photochemical, so it's conrotatory. Gives pre-vitamin D3. There is then another pericyclic reaction that shifts a hydrogen from here, this methyl group across to here, a 1,7 hydrogen shift, and sigmatropic shifts like that I'll mention tomorrow. But that then makes vitamin D3. So this is pre-vitamin D3 from the electrocyclic ring opening here, followed by a sigmatropic shift. Now we depend on that. Lack of vitamin D3 causes rickets, which is more of an issue with Asian people, first generation in the UK, than it is with native Westerners, although it's not unknown if you are vitamin D deficient. I think something like 20% of the population in the UK are deemed to be vitamin D deficient enough that they should take a supplement. Certainly, and more among women as well, who are prone to osteoporosis fibrosis, thinning of the bones, because the vitamin D3 is connected with complexing calcium and helping absorb calcium into the body. So my wife takes vitamin D capsule every day. So I keep telling her this is what's going on. Get out in the sun a bit more. She says, I would if I could. Okay, so this is a real-life biochemical example of an electrocyclic reaction, and it does obey the molecular orbital rules, the con rotation, dis rotation. So these are not as generally applicable in synthesis as the Diels order and 1,3-dipolar cycloadditions, which is why I haven't included quite so much material on this, but you need to see these to see how, to see the difference with photochemical reactions, where basically the rules are always opposite to what you get for thermal reactions, and to see the electrocyclic reactions, just to see that you can translate the kind of orbital analysis that we've been using into a different class of pericyclic reactions. So I knew that would be shorter, so that's fine. That's the end of today's sessions. Thank you much. We'll continue tomorrow at 10 o'clock, I believe, again. 10 o'clock. 10 o'clock. Okay? Same place, same time.
Okay. Right.